Right, so this is going to be hopefully the last installment of quantum groups at roots of unity. So let's just recall a bit from last time. Kind of final thing we said. So you remember we, like always, we fixed a reduced expression for the longest element. Then for each such fixed reduced expression, we have an A basis of Lustig's divided power form of the quantum group, given like this. Okay, so here I've totally ordered the positive roots with respect to this choice of reduced expression. So when I run over the basis, I go in the chosen ordering in the positive roots and in the reverse ordering for the negative roots. And let's just recall that these algebras, we define these, the U plus and the U minus, to be the subalgebras generated by the divided powers. And actually these really do span these algebras. So they really give it these pieces of this basis really give a basis for this UA plus and UA minus. So the most difficult part about proving this, or kind of the whole crux of proving this, is that what we need to show, or what Lustig showed, that you actually have an action of the braid group on the algebra UA. So so the braid group you actually gives you have a homomorphism as algebra automorphisms of this integral form. Okay, so once you know that the braid group acts, right, so it actually preserves this form, then defining all these things is not too tricky. But that's really the difficult part. But we'll just want to remember that that we have an action of the braid group on this algebra. Okay, so for okay, so the algebra UA0, so we want this triangular decomposition of Lustig's form, and so we now define an A subalgebra just from the basis, so we can just take the span of the relevant part of this triangular basis, and that gives us what we want for this UA0 algebra. Okay, so in this way, we get a triangular decomposition. Okay, as we would hope for. Or maybe the other way around, I should say. Okay, so I just wanted to mention something about vermas and integral modules.
Oh, this is a class.
Okay, so we look at modules. Well, you can, if you want, you can do it. We can do it as in Lustig. So we can kind of consider the category. So Lustig. The category C of type 1 UK modules. Okay, so each
remind what K is.
Right, so K is going to be the fraction field. Right, so maybe I should say, okay, so just as a reminder, so K is the fraction field. Well, I guess, yeah, we can do it like this. K is the fraction field of A, which is the Laurent polynomial ring over my fixed variable. So we could also work over CV if we wanted to, because the algebra's integral. We can also just work over QV. Okay, so we have these type 1 modules, which should have a weight decomposition, right? So these have weight decomposition. Right, where we run over the weight lattice.
And here we are talking about finite dimensional modules.
Yes, I guess in Lustig's book he considers all modules with. I mean, he just looks at the category of all modules, possibly infinite dimensional with a weight space decomposition.
Okay.
Or they're finite dimensional. I can't remember. I thought he included infinite dimensional modules, but maybe they're all finite dimensional.
Well, I mean, if we are to talk about verma modules, then verma modules are definitely infinite dimensional.
Yes, that's what. Yes, so I want my modules to be possibly infinite dimensional. right? Just modules with a weight space decomposition.
Okay.
Okay, so I'm just the weight lattice. Okay, so inside here we have integrable modules. So say M is integrable. If any M and alpha in pi, there exists an integer such that, right, so we want a kind of local, kind of a local nilpotency. So you want it to kind of be that the E's and the F's should act, should be nilpotent on this module. Okay, so in Leonardo's talk, right at the beginning, we saw that we have verma modules. So for each lambda and lambda, we have a verma module. Okay, which is defined as UK modulo J lambda, where well, this is given like this. So the verma module does have a weight space decomposition, but it's not integrable in general. So okay, so let's just remember it does have an integrable quotient. So
Well, if lambda is dominant,
right.
And when lambda is not zero, this quotient is zero.
Does it need to be dominant for this, to have the?
Of course.
Right, because yes, okay, yes, it should be dominant. Yes. Okay, so let me just say this and then. Okay with this. Okay, so if lambda is dominant. Okay, so the thing that we really want to say about these verma modules is actually that the Lustig form gives us integer forms for the verma modules. Okay, so one kind of way to see this is that, right, so we have an isomorphism of K vector spaces, right? So you can basically just identify this this verma, right, with the lower part of the quantum group. Okay, but now we actually have, I mean, the thing on the left has an integer form, and so this is going to give all the vermas an integer form, right? So the image of UA minus okay, so this gives you, this is how you can consider, so you need to check some things with the commutator formulas to be sure that this is really this really works out, but this is okay. And so in a similar way, one also gets right, so one also gets integral forms of these quotients. When lambda is dominant.
And the integral form for the quotient is just the image of the integral form in the verma model.
Exactly. So exactly. So you just extend this. You have this now, this quotient here, right? And the integral form is just given by taking UA minus and passing into the all the way down to this quotient. Okay. Okay, so we have integral forms of these modules, and we can also talk about the R matrix. Okay, so right, so this was the main content of Elijah's talk. We have an element theta which lives in a certain completion of the quantum group. So you can kind of avoid talking about this. And Elijah's talks didn't really talk about the completion, because if you just talk about the theta mu's individually, then you don't have to talk about the whole infinite sum, which means you can avoid talking about this completion. But if you're willing to complete, then you can make sense of what this infinite sum should be. So you really should think of this as an object in the completion.
Sorry, can I just go back and ask, like, what would happen if we try to define this integral form of the verma using Cauchy-Concini form? Like, what's the deal with the two versions of the quantum group?
Well, you would have you still have verma module of the Concini cuts, and there are two different forms of the same verma module of K. So the representation theory is going to be crucially different, because the Concini cuts form has a large center, and Lustig form does not. So somehow verma modules for the Concini cuts form, they don't play the same role for the Lustig form.
For what? Play the same role for what?
They don't play the role that they play for Lustig's form, because for Lustig's form, every finite dimensional irreducible representation is a quotient of some verma module. For the Conchini-Katz form, that's not the case. That's the same thing which happens in characteristic P when you talk about algebraic group and the D algebra.
Mm-hmm.
Okay, so this this element theta, right? So this satisfies, right? You basically characterized by the fact that it should intertwine the co-multiplication up to this Tor, which is this kind of anti-automorphism that we saw in the in Elijah's talk, which fixes E's and F's and inverts K's. Okay, so what we really want to say is that there's an integral form of theta. So let's just kind of go back and be a little bit more specific and just reminding what how we construct this basis for UA. So let's just specifically write W0 . Okay, so we construct a positive root. And these divided powers are constructed by applying these Lustig's T operators to the divided power of the corresponding simple E's and F's associated to the simple root. Okay, so in Calder's talks, we saw, Pavel had made this comment about there being a kind of simple expression for, or nice formulas for theta. Calder talked about this right at the end of his talk. So, right, so in Calder's talks, we saw, well, with slightly different notation, but almost this not too different. Okay, so theta is actually going to be a product of terms indexed by the positive roots. And so you kind of remember, like, Janssen doesn't actually state this equality in his book, but that's because he's avoiding working in the completion. So does you actually get like an equality here? Okay, so theta J is given like this. Okay, so one thing that might look a bit different in Calder's talk was this factorial was on the bottom, not up here, but that's because he didn't have the divided powers. So they've slid one of the denominators into one of the divided powers, and then there's another one on there. So
I suspect that S and R should be the same letter.
Oh yeah, thank you. Yes, that should be an S. Thank you. Okay, so Ivan pointed out at the time when we talked about this that it was kind of useful to note that there were sort of only divided powers involved in this expression. And so what we see here actually is this this element clearly lives inside Lustig's integral form of the okay, so okay, well, not exactly in the tensor product, but some completion of the tensor product of Lustig's form. But this means that theta also lives in this completion. Okay, and so the components theta mu, those will also live in those will actually be contained in the Lustig algebra, because these are just kind of obtained by calculating just from this expression. Okay, so okay, so once we know this, the R matrix, so this is going to mean that the R matrix lives in really genuinely inside this integral form. And so you can just specialize the integral form to get the R matrix at any over any specialization of this.
Well, this requires a little clarification. So in R matrix, there are two factors. There is this interesting factor theta, and there is a Cartan part. Mm-hmm. And of course, if you want a Cartan part, then Cartan part will act on modules with weight decomposition. So if you have a dominant, if you have a weight, then a weight naturally determines a homomorphism from UA0 to A. And that's essentially by well, I mean, well, am I saying this? Yes, because the binomial coefficient of power of V is Laurent polynomial in V. There is divisibility. So and so if you have a module with weight decomposition of type 1, meaning that all weights, so we have a module over A, and it should decompose into the direct sum of A submodules, where UA0 acts as prescribed by weights. So on such a module, we'll have an R matrix. And then I guess one can prove that integrable module will have such a weight decomposition. This should be the picture. Because so far, we only know that theta acts on an integrable module, but we also need the action of Cartan part to talk about R matrix.
Right, yes, okay.
So this may be somewhat explicit, somewhat implicit in Lustig, because Lustig deals with idempotent version of the quantum group. And then, of course, if you have idempotent version, then you can write this, You just need to say how this carton part acts on each weight space, and it's, you know, we've essentially had that in a larger stock. But if not, then we still need to define that element, whatever it was denoted. Maybe Elijah remembers. I don't.
I don't remember either.
Okay. But it still needs to be produced. So maybe in the final version of notes, Jay can make some comments on this.
Yes, I can add something.
But the point is, so kind of one, so maybe we can get a little bit back. So we had this easy to define Cas-de-Concini form, and Cas-de-Concini form, as you know, any reasonable form, is a Hopf algebra, but it doesn't have braiding. It's precisely because if you look at formula for theta j, there are denominators. So J wrote it in such a way that there are no denominators, but that's because he uses divided powers. And if we don't use divided powers, then we will have S quantum factorial in the denominator. And it just doesn't lie inside of the Cas-de-Concini form. And you can actually see that the Cas-de-Concini form has no chance to have a braided category of modules. But the Lustig form has an R matrix. So the category of integrable integrable weight modules of a Lustig form is a braided monoidal category. And that's, if you want one single reason why Lustig form is better, it's this one.
Is there no way to define a braiding?
Well, you'll have examples of modules which are where tensor products in different directions are not isomorphic.
No, there is a way to define what is called a meromorphic braiding, which means it's going to be have some poles. It will depend on the central characters and will have some poles at the points where these tensor products are not isomorphic.
Right, but there are still.
It's not a braiding, but it is something which is also very interesting.
But can you maybe say that? So in the like positive characteristic version, right? So if I think of the you know, I want to think of these forms as being analogous to like the universal enveloping algebra, the Lie algebra, and then this distribution algebra, right? But like the universal enveloping algebra, the Lie algebra in positive characteristic is still, you know, I can still take representations of that, and that will be a symmetric monoidal category. So why is there not a braiding when I try to do the Q version of that?
Well, I mean, there are poles. So there, I mean, you need not only, so to deform, you need not only a braiding, but you need a Poisson structure. And so, so what will happen is you are going to get poles with respect, so this thing is going to have poles as with respect to central characters. So generic representations for them, our metrics will exist, but this will they will have singularities.
But I guess my question is, why doesn't something like this happen if I take representations of a Lie algebra in positive characteristic?
Well, because poles, well, I mean, morally, I think the poles exist, but they live outside of Q equal 1, right?
Yes. I mean, well, there you don't have to define an R matrix. It's just a symmetric monoidal category. So,
all right, I'll take that.
But you can compute the what happens to this R matrix when you degenerate to characteristic P and see what happens to those poles. It's actually interesting. I haven't seen this done anywhere.
Okay, maybe we can continue this stuff.
Yes. Okay. So maybe I'll also say that the argument for this given in Lustig's book is quite different to the argument we've given here. So in some senses, well, or it seems different to me. Maybe it's not different if you are an expert, but I mean, he uses the existence of, I mean, he has a canonical basis for, so obviously you get all the bases we've looked at so far with respect to these choices of longest element, and he has a canonical basis, which is with respect to one such choice of, which he identifies as longest element. And he uses this together with the fact that the vermas and these integrable quotients have integer forms to actually deduce the fact that the R matrix lives inside his integrable form. So it's a bit of a different argument, but yeah, I just wanted to mention that. Okay.
So maybe I could sketch yet another argument. So in Calder's talk, there was a remark on how theta is written in terms of this dual basis in U plus and U minus. And what you can show is that this pairing that was introduced in Arun's talk and then used in Calder's talk, it gives you a perfect pairing between U plus Lustig and U minus the Concini cuts. And so in particular, you see is that when you write the quadratic element which corresponds to this pairing, in particular, it lies inside of the Lustig form. So for this, you don't need to know the decomposition of theta as a product, but it still gives you an inclusion of R matrix into the Lustig form.
So I mean, Lustig's canonical basis is kind of,
well, I mean,
from
this all
what I
depends
understand,
on what you know
almost,
and what you want to
it's
use.
like.
So I imagine that once you have a canonical basis, then you can just use it for these purposes. But that's certainly not the easiest proof that you can give.
No, yes, I do appreciate it. It's very difficult to prove the existence of the canonical basis. But no, I was just curious about if there's a relationship between, I mean, if these are, I mean, Lustig's canonical basis is defined to be kind of almost self-dual with respect to this pairing, right? Like, so is that, do you like, I mean, if you actually have a pairing between the Deconcini cats, do you kind of understand the relationship between the canonical basis and this thing coming from Deconcini cats, or do they just live in two totally different worlds and you don't know how they relate to each other?
Well, I never thought about it, but well, I mean, when you pair two canonical basis elements, I imagine that you will have some denominators. So the good thing about perfect pairing, you know, is kind of, is there is a whole lot of, you just kind of choose a basis in one space and then you automatically get basis in the other space. But you don't have any limitations on what basis in the first space you choose. And canonical basis is a pretty difficult basis, right?
Yeah, yeah, yeah. Okay, so let's talk about the quantum Frobenius. So what one should imagine as the motivation for this, and we'll really kind of make this point at the end, is one should have in mind this calculation that Ivan did on the distribution algebra, where you look at the Frobenius acting on the distribution algebra. So this, kind of in a very well-defined sense, one can consider the quantum Frobenius to be a characteristic zero lift of the Frobenius one sees at the level of the distribution algebra. Okay, so let's try and do some things, and then
maybe one should emphasize that this lift business will only apply to piece roots of unity.
Yes, yes,
So
yes.
Indeed, and it's one of the reasons why quantum groups not only provide an analogy with characteristic P story, but also provide a tool to study characteristic P story, is that Lustig's form and in fact Kazda-Concini form at piece root of unity is closely related to the corresponding algebras in characteristic P. But of course, quantum groups also make sense at all other roots of unity.
Right, so with this in mind, let's fix an integer L, not necessarily prime. So we'll do this Lustig style, and we'll let AL be the quotient of this Laurent polynomial ring by the ideal generated by the L cyclotomic polynomial. So kind of another way to say this is that AL is the integral group ring of the cyclic group of order L. Okay, so your element inside V inside AL now has order L. Okay, it's an element of order L. Okay, so just for notation, let's let L alpha be the order of V to the 2D alpha in AL. And so for brevity, I'm gonna let U sub L denote the specialization of this algebra, okay, over AL. Okay, so let's just consider the case of G equal to SL2 first. So maybe it's handy to start with an observation about this algebra UL. So we've kind of seen this phenomenon coming up before, right? So in UA, we have the following identity. Which is easily deduced from because we know exactly what this this defines this element in over the fraction field. Okay, so, well, if we now specialize, so in UL, the left-hand side is obviously 0, which means the right-hand side is also going to be 0. So here's an easy exercise. So in UL, the right-hand side is k to the L minus k to the minus L if L is odd. And it's v to the it's given like this when L is even. Okay, so if L prime is the order of v squared, then we get the k to the 2L prime is equal to 1. Okay, so in these specialized, Ivan's pulling a face, which means I've probably done something wrong.
I'm a little bit confused. So if we know that the square of this element is 0, why is the element itself 0? Somehow.
Because this has zero divide. It has this algebra has 0 divisors, right?
Right, which is demonstrated by the previous identity.
Yes. Okay, well, at least in the odd case, this argument is okay.
That's this I certainly agree.
Okay.
And perhaps
So-
the even case requires a little bit of work. Well, I mean, the algebra has 0
Yes.
divisors, doesn't
Okay,
mean
maybe
that it
the-
has important elements. So maybe. So I don't remember whether this, well, especially in this kind of specialization, I don't remember whether it has important elements or not. But I guess, especially in the case of SL2, perhaps it's not so difficult to check.
I think at least that this, well, even if this argument doesn't work, I think this is still true. And
Yeah, it looks like this
in
should be true.
the even case, I think this is still true.
For even L, shouldn't you plug just L over 2 in the left hand in your left hand side of the page at equation? If you plug it in for L over 2, you still get 0 on the left hand side.
Yes, this sounds right.
Ah, right. Yes. No, this is yes. Okay. And then that should give me the right identity.
And we can even say which factor is 0.
Yes.
Yes.
So yeah, it
okay,
should be fine.
Okay. Okay, so I think the exercise is still correct. The statement I wrote down is still correct. But
maybe you can add another bullet saying improve the exercise.
Or maybe exercise. Okay. Okay, good. So in this, okay, so in this algebra now, these k terms are going to have finite order. Okay, so
maybe I can just make a comment. So when we talk about distribution algebra, let's say of SL2, then we have the identity like h to power p is equal to h. And the identity k to power 2l prime equal 1 is precisely the multiplicative analog of this, because the identity hp equal h tells us that h will act semi-simply with eigenvalues from 0 to p minus 1, which are all possible residues. And the identity k to power 2l prime equal 1 will tell us that k will act semi-simply with corresponding eigenvalues, with all else root of unity. Well, you need to restrict to type 1 representation, strictly speaking, but up to some technical nonsense, what I'm saying is correct.
Okay, so we kind of discussed this
Jay,
previous.
what would be a good time to make a break?
Let's break now before we get into.
Okay, let's have a break until 5:05. And meanwhile, if people have questions, maybe they can ask them. Do people have questions? Jay?
Yes. Okay. Right. So we're going to use a specialization of this algebra, which we kind of did before. We kind of observed before that, I mean, we can specialize at any root of unity. In particular, we can take that root of unity to be 1 or minus 1. Okay, so and those roots of unity also have the advantage of being in the integers. So let's let epsilon be plus or minus 1. So I'm kind of doubling up on my notation, but you'll forgive me, I'm sure. So I'm going to let u sub epsilon be z sub epsilon right. So I'm just going to tensor with the A module with V acting via epsilon. Okay. Okay, so I'm going to want to slightly change the parameters of my algebra. So we're going to let star from A to A be the unique ring homomorphism such that V star is V L prime squared. Okay, and then we get an algebra UA star, which is the same as UA, but where we've replaced V by V star. Okay. So really we're kind of specializing UA over this by specializing P. Okay. And then this can be, this algebra can also be specialized at epsilon, okay, at this plus or minus root of unity. Okay, so this is basically going to be, so I'm going to think of this as an AL algebra. Right, this can be tensor over, what do I want? I want U epsilon star, and this thing is Z epsilon. Okay, so Lustig's theorem, so let's just state it like this for the minute. So assume L is odd and G is SL2. Then there exists a unique AL algebra homomorphism FR
What is the subscript?
It's
I just haven't read it.
it's 1L. So I'm taking epsilon equal to 1. So so V is acting via 1, and then I'm specializing over L.
And what does this mean in pedestrian language? What is this algebra?
Well, I mean, for instance, in this algebra, then like the k's will square to 1, right? Because this is you're letting, right? But I mean,
just so
you want this to be a homomorphism of so morally you have a map from UL to U1, right? But you have to kind of tensor with AL because you want to say that it's going to be a homomorphism of AL algebras.
So if I were just to specialize to a field instead of specializing to this AL, then I will have a homomorphism from specialization U epsilon to specialization U1, right? So I can base change to
exactly,
C and then just evaluate at my favorite primitive L's root of unity. So I will get algebras over C. And this will be a homomorphism from U epsilon to U1, and U1 is a classical universal enveloping algebra adjoins this guys who just square to 1 and don't talk to anybody else. Right?
Yes. So you should think about this as, so I mean, if I was phrasing this over C, then you would think of this as the C algebra specialized at an Lth root of unity. And this is the C algebra specialized at 1, which, as you say, is the universal enveloping algebra adjoins some central elements that square to 1. Okay.
Thanks.
Thank you. Please make as many comments as many clarifying remarks as you want during this entire section. I'm very happy to have them. Okay, so really, as I said, this is motivated by the distribution algebra calculation. So what should this quantum Frobenius morphism do? Well, it should just do what the what happens what we've already seen.
But in this case, L prime and L is the same thing, right?
Yes, yes. So I want to say that L prime and L are the same, but I want to set it up in a way that means that I don't have to rewrite it a second time. So,
Okay.
But when when L is odd, L is equal to L prime. But when L is even, that wouldn't be the case.
Okay.
But yes, in this setting, okay, and so this quantum Frobenius just fixes the case. Okay. Okay, well, the unicity of such an AL algebra homomorphism is clear because these generate the algebra. So the hard part is showing uniqueness. Okay, so
You mean existence?
Existence, sorry, yes. So the difficult part is showing existence, and so there's well, Lustig proves more than just establishing a basis for this algebra, an A basis. He gives a presentation for the algebra via generators and relations. So it's enough to, define FR on the generators and then check that the relations hold. Okay, this isn't quite how Lustig does it in his book. He has it's slightly different, his argument in his book, but this is how he did it originally. So let's try and follow his original method. So basically, I mean, this tells you exactly what should be happening on the plus part of UA, on the minus part of UA, but actually what's happening on UA0, because it's still a little bit mysterious. You have to say it. We should say a little bit more. Okay, if we want to kind of think of it in this triangular decomposition, UA0 has more generators, so we have to kind of specify what's going on these extra generators.
Actually, maybe I can make a comment. So if you allow yourself to work over a field, then your life simplifies. Well, characteristic zero field. Because then your algebra will just have two generators E, which will be E divided power 1 and E divided power L, two generators F of the same nature, and then invertible generator K. And you can, it's not so hard, but it's somewhat tedious to write relations on these elements. You just see that this is a homomorphism.
Right. So okay, so let's just recall that UA0 is generated by K plus minus and K0T with T greater than or equal 0. So define FR on UA0 by, well, actually, we already know what this should be because we know the calculation from the distribution algebra. Right, so it should just divide t by L prime if L prime divides t, and it should be 0 otherwise. Okay, so the first question is, well, what so we're certainly not going to check all relations for this morphism, but I want to just do one or two which are kind of instructive for this thing. So let's first say what is this? Well, what should this be? Well, we need an expression for this element in terms of these generators that we wrote down, and in UA0 we have that this is given like this. Okay, so we want to try and
T minus
understand
J,
what
right?
the T minus J,
Minus
yeah.
somehow
T minus,
degenerated to the point.
okay, so it should be T minus J. Okay, so if I'm going to apply the quantum Frobenius to this, well, this dies unless T minus J is divisible by L prime. Okay, so let's write T equal to T0 plus T1 L prime. Okay, so the image of this element under the quantum Frobenius, well, it can be written like this. Okay. So this is just simple using the definition of what we wrote down on the generators. So, but many of these coefficients here are going to die. So it's a kind of fact. Okay, so if L prime does not divide T and L prime divides C, then CT is 0 in AL. This is proved in Lustig's book. Okay, so if L prime does not divide T and L prime divides C, then this term gets mapped to 0 by the quantum Frobenius. Okay, so let's so the other case we kind of need to understand is just when L prime divides T and L prime divides C. Okay, so T is equal to T1 L prime and C is equal to C1 L prime. So we need another fact about these quantum binomial coefficients. So no matter which way you kind of slice it, it seems that these are kind of the two important things you need to know. So if L prime divides C and L prime divides T, then okay, so these elements are equal as elements of of AL. Okay. Okay, so if we do kind of the so let's see this. Okay, so let's write C is C1L prime, right? And T is T1L prime. Okay, and we apply the quantum Frobenius to this. Okay, so it's actually at this point, we're going to use the fact that L is odd. So it's at this point here, because what I want to be able to do is to take my K to the minus A L prime, and really I want that to be K to the minus A. So the image of the quantum Frobenius lands in this specialized algebra U1, where K squared is 1. So when L is odd, L is L prime, then actually that means that K to the L prime is just going to be K. So I can replace this by K to the minus A, which I can't do in the even case. Okay, so okay, well, V to the L prime squared, that's my V star, right? That's where this star is coming from. From what I just said, we can get rid of the the L primes. But now this formula that we wrote down before, that should be C1. This is going to tell me that this is exactly C1 T1. Okay, so when the terms here and here are divisible, both divisible by L prime, then I can kind of, the quantum Frobenius will kind of cancel it out, and you'll get left with this.
Sorry, can you remind me what this star thing is doing?
So the star thing is just replacing V by V to the L prime squared.
So if we don't want to be fancy and work in specializations to characteristic zero field, such as complex numbers, then the star just sends epsilon to 1.
Right. So in particular, like this binomial coefficient star is like an ordinary binomial coefficient. If I do
That's
that.
right.
All right.
So
Yes.
what's going to happen is that this binomial coefficient K0L will go to H, and this binomial coefficient that J is considering will go to H plus C1, or something like that.
Okay, so let's just kind of briefly have a look at the relations. So just to kind of, certainly not going to list all the relations. Let's just say some of them. So okay, so maybe the interesting relations for UA are okay, so this is basically the relation that defines the plus part. Okay, and then versions of, right, there'll also be F versions of 1 to 3 with E replaced by F and suitable sign changes. Okay, so this relation holds when you apply quantum Frobenius is an immediate consequence of this fact about binomial coefficients. So that interesting cases when L divides both S and T, but in this case you can kind of cancel the L's on the on this coefficient. Okay, and so this relation at the bottom is where you need to understand what happens, what the image of this is under the quantum Frobenius, and it's not too tricky to work out. So I'm just going to leave it as an exercise. Right, just to check that 4 holds. Okay, so do you want to make a comment?
No.
Okay.
If I want to make a comment, I make a comment.
Okay. Okay, so really this tells you that okay, so this is going to satisfy the relations, and this is going to tell you that this quantum Frobenius exists. Okay, so what about the even case? Well, in some sense, the even case is different, and the difference is that so if we kind of go back to this theorem, right? So in the odd case, so this algebra specialized at 1 was coming from the same Lie algebra that that we had before, but actually when what Lustig observed is, or maybe someone else observed it as well, I don't know, but it's certainly in Lustig's book, that actually you should change the Lie algebra that you work with when you pass to the even form. So instead of working with the we are working with the simply connected form, we should swap this for the adjoint form of the quantum group. Okay, so and so in some sense this makes.
Doesn't this depend on parity of L prime?
Yes, so when it's even, yes, so that it does depend on the parity. It does depend on the parity of L prime, but let's say it's 2. For let's say or that.
Well, I mean, we don't have that many roots of unity for the 2. Ah, you mean L prime is equal to 2?
Yeah, let's say L prime is equal to 2. Okay.
Right. So the difference is somehow. Well, maybe we shouldn't discuss this in the case of SL2 because it's not too impressive. Maybe you can explain us what happens in the gel case.
Yes, but maybe I just want to say that, like, kind of morally, maybe, or what happens is that, or the way, I don't know, the way I thought about it, and is probably wrong, but in the even case, you'd quite like that the sort of the roots, that when you take so in the simply connected form, you're looking at k alphas coming from the root lattice, and when you map them under the quantum Frobenius, ideally it'd be great if these became squares, Well, in the case of SL2, that would happen. They are kind of squares of elements, like because the simple root is twice the fundamental dominant weight. And I think this is kind of, it helps repair some issues that are happening in this when you try and do this in the even case. Okay, so let's just kind of say a little bit about what happens in general. So so Ivan is right in that more interesting things happen in the general case. So you get that you actually change, or it's not just that you change the form, as in you choose a different isogeny type of the group, or you're in this different sublattice of the weight lattice. You actually should in general change even the root datum that the kind of root system that you're working with. You should actually go to the Langland's dual. So in some cases. Okay, so in general, Lustig does the following. So let's just kind of recall that, well, the way we defined it, L alpha is the least integer such that is that this term is a multiple of L. So Lustig constructs a new Cartan matrix, or a new form, just by scaling with respect to these L alphas. So so you get a new form. Okay, and so with this new form now, your alpha alphas, so you're going to change the length by multiplying by L alpha squared. Okay. Right, so you get a new Cartan matrix.
So in the inclusion sign, should I have L or L prime?
Sorry, say that again. In which?
In line number 3, is it L or L prime? So I always thought that, you know, the case of 2 times. The case of 2 times odd number is not very different from the case of odd number. Is that instead of U1, your quantum Frobenius lands in U minus 1, but U minus 1 is not very different from U1. And you pass to Langland's dual when you have L divisible by 4. Well, maybe
yes.
it's not much different. Because if I just don't divide L by 2, then all L, you know, if I rescale L, then all L alphas get rescaled. And this doesn't really change the Cartan type.
Well, I mean, L alpha is the order of V2D alpha, right? So when in the simply laced case, then the L alphas are just L prime.
Well, they're all the same, and that's what's important. Well, maybe that's kind of Well, let's skip this discussion because I don't think it's important.
Okay, so you're going to get a new Cartan matrix. So really, let's just say maybe when we think about this, you think of the forms, because we're in the we're in this simply connected case. So we have a perfect pairing, right, which for us comes from right. So we have the root lattice, which you could say with the co-weight lattice. Okay. Right, and so when you do this with evaluate this pairing at roots and co-roots, then you get the Cartan matrix. Okay, when you look at simple roots and simple co-roots, so you get a new Cartan matrix. Okay, or a new pairing by setting alpha beta star right, and so now this is going to become 2 times alpha beta L beta over alpha alpha L alpha. Okay, so you can kind of see that if in the simply laced case, all these L alphas, right, all the D alphas are equal to 1, so all the L alphas are equal, and so really I didn't do anything to these Cartan integers, but it's now but now if actually these D alphas are different, then these L alphas are going to be different, and this ratio will in fact actually change the Cartan integers. So you're going to get this form, or this new form will actually give you a different possibly a different type of algebra, or a different root system. Okay, so what you want to do is come up with a new lattice. So in the case of SL2, you would want to kind of swap the root lattice with the weight lattice. So okay, so Lustig does this as follows. So he considers okay, so here for us, X is going to be the weight lattice. Okay, and then you just take y star to be the dual. So if you think about X and Y, so you have a kind of a pairing between the weight lattice and the co-root lattice. Okay, then I have to flip things around because it's Yes. Okay, so you have a kind of natural embedding of the simple roots into X star. You just scale. Okay, so your root should go to L alpha alpha. Okay, and then what should the co-roots look like on the dual side? Well, the co-root should go to it's kind of an embedding into Y star. Okay, so let's just look at this condition in the case
I don't understand what's right here.
of S.
What's alpha star? Why is it equal to something? Is it alpha check goes to that expression?
Yes, I want to be that. I want to be that. This is alpha check. Yeah, so this should be, thanks. This should be kind of my new alpha check. Like my new co-root should be this in Y star. Okay, so if you, in the case of SL2, you have just right. So y is just Z alpha. There's only one simple root, and X is Z omega check. Okay. Okay, and then the pairing is just alpha and omega check are in duality. Okay, so when this L alpha is odd, nothing particularly interesting happens. But when L alpha is even, okay, so if L alpha, let's say, is 2, okay, then X star is genuinely going to give you the kind of co-root lattice, right? So you're going to get Z alpha check because alpha check is 2 omega check. Okay, so you'll actually change this this lattice. Okay, so you actually get a new lattice, and right, and then the dual of this lattice, right, of the co-roots is just going to give you the weight lattice. So you're kind of swapping. Okay, so in this case, you're swapping the simply connected and adjoint forms. Okay, so there's a process by which you can construct this. So I mean, in general, Lustig works with root data, but I mean, you can also just think about it. If you're just working in the semi-simple case, you can just think about it in terms of subgroups of the fundamental group of the root system, and in terms of lattices. We don't need to work in this full generality of root systems. of root data in the semi-simple case. Okay, so in general, Lustig's quantum Frobenius. So okay, so the quantum Frobenius is defined as before, right? So in exactly the same way, you
Sorry, what's the generality?
Well, I think if you, so you can do this for well, any G. Okay, so if any semi-simple G and any L. Okay, so you get, so you associate to G a different Lie algebra via this process, which depends on L. Okay.
But it just explained us that it's not about Lie algebras, it's about root data.
Yes, so
the Lie algebra,
yes, so
it's clear what's going to happen with Lie algebra if, you know, L is odd or is 2 times odd, then G star is G, and otherwise it's length as dual.
Okay, so well, let me say it's a different form of the quantum group. So, well, let me say it's like this. It's you have G gamma. Okay, so gamma is something sitting in between the root lattice and the weight lattice. So to any such gamma, you have a corresponding form of the quantum group. And via some construction with root data, you can take your pair G gamma and you get a new pair, G star gamma star. G may be equal to G star, or it may be the Langlands dual of G. And gamma star is a different lattice inside the weight lattice for that dual Lie algebra. Okay. So now the quantum Frobenius is an AL algebra homomorphism okay, so this should go from the original algebra specialized at an Lth root of unity. And it lands in this algebra U epsilon L star is as before with epsilon equal to plus minus 1, and whether you're in the plus or the minus, that's going to depend on the order of whether L is even or odd.
But wait a minute, the formula is still that it's your root of unity to power L prime squared.
Yeah, so I mean, this should be.
So if we are odd or divisible by 4, then it's 1. And if we are congruent to 2 modular form, it's -1.
Yes, exactly. Yes. Okay. Right, but this is defined with respect to this new pair in the semi-simple case. But the quintessential formula is the same, that you take a divided power and you either replace it with, you replace S by S over L prime if it's divisible by L prime, and if it's not, then you, then it goes to 0. Okay.
So on root SL2s, it's defined as quantum Frobenius for root SL2s, keeping in mind that roots have different lengths. So the L primes for different roots will be different.
Yes, exactly. Yes. So it's like an SL2 calculation, but then you have to take into account that the L primes are different for different SL2s.
Okay. And the check is just a long fun with relations.
Yeah, so somehow, yeah, it's, you just have to, I mean, yes, you basically do just have to do I mean, I think Lustig's argument in his book is a little bit slicker. He has some like slightly more clever ways to do the calculation.
Well, I mean, the hard part, I imagine, is what happens with Serre-like relations and their consequences.
Yeah, exactly. So, but I mean, at some point there is, I mean, even for small primes, when like for G2 in characteristic, when L is 3, I know he kind of has to fall back on using the fact that he previously calculated a presentation for the positive part of the root of the quantum group, and there he has to check generators and relations.
Mm-hmm.
So it's, his argument doesn't cover certain small cases, and there you really have to just go back to his kind of original argument in his paper, which is you just check generators and relations. And it's just that the generators and relations become more ugly as well, I say ugly, other people would say more complicated, but yes, it's just, there's more stuff to check.
Okay. All right. I think it's time to finish.
Yes.
Let's thank Jay for the talk. Questions?
I have a question. It's probably a foolish thing, but you know, it's April Fool's. So if I have a quantum group at a root of unity that is of order like a product of 2 primes, let's say 2 odd primes, can I define a sort of partial Frobenius twist with respect to one of the primes? So in particular, what I think I want is I want to go from the integral universal enveloping algebra at this root of unity at say order PQ. I think there should be a map to something in characteristic Q at a Pth root of unity. like a Frobenius map that way, but you also have to reduce characteristic.
Somehow,
Yeah, there is a thing like that. I mean,
Do I get some sort of like reciprocity between, say, like quantum group representations in characteristic 5 at a third root of unity and representations in characteristic 3 at a fifth root of unity? At least for like some sort of class of restricted weights?
no, because you will have things in characteristic P. You will also have things. Okay, maybe for restricted weights, maybe, but I don't know. No, but I mean, you can simply reduce your quantum group to if your root of unity has the order PL, for example, you can reduce it mod P, and you will be at a root of unity of order L in characteristic P. And there
well, somehow like there's a nilpotency thing, right? If I take like, you know, if I just quotient out by a PL cyclotomic polynomial and then I reduce that mod L, I get like, you know, it's the pth cyclotomic polynomial to the Lth power, or whatever.
well, so you have to reduce when you reduce mod P, you really don't reduce mod P, but you reduce modulo some root of P, root P to the power 1 over P or something like that, or maybe 1 over P minus 1. Anyway, what does it mean to reduce mod P? This means you have cyclotomic field or ring, and you will complete it and you get some kind of p-adic ring, but that ring is ramified and you have to quotient by its maximal ideal. So it's not generated by P. What is generated by P to the something like 1 over P minus 1.
But I guess I wanted to do that. I wanted to take care of that by doing a sort of Frobenius map on my like quantum group, right?
So in characteristic 0, I don't think you have this map, but in characteristic P, definitely, if you have quantum group in characteristic P, you have the first Frobenius, which is Lustig's, and then you can follow it up with any power of ordinary Frobenius.
Yeah.
but it's not what Nate is asking, right?
Right. I think what I want to do though is I want them to be sort of simultaneous, right? I want to like I'm taking like a degree 5 kind of map, but then it goes from the integral thing to a mod 3 thing. But so it behaves like a Frobenius in sort of one way, but not the other.
How about we declare the self-service establishment, and you know what it takes to establish such maps.
Yeah.
And,
I should say that there is so people in infinity categories and homotopy theory, they discovered that Frobenius, usual Frobenius in algebraic geometry, can exist in characteristic 0 or over Z if you work with infinity categories. So this is a paper of Nikolaus and Scholze. And then you can somehow do things with Frobenius in over the integers. So that's a very useful, apparently, but difficult technology.
That's too many categories. Infinity categories are. That's too big. I can do 2 categories. That's about it.
Okay. Anybody has any other questions?